In any cryptographic system that you deal with, there are going to be two incredibly important artifacts: the private key and the public key. In Ethereum, your key pairs are your lifeblood. So before doing anything else, it's important to understand how they work. And I think this is going to be easier to wrap your head around if I show it visually. So I'm going to set up a quick demonstration. First, I'm going to create a new folder called Keypairs, and then I'm going to cd into it. Then I'm going to create a package.json file, and underneath dependencies, I'm going to add web3 the same way that I did in the previous video, and version 0.17.0 alpha, but I'm also going to add the library Ethereum util, and that is version 4.5.0. Now, the Ethereum util library is a helper library that provides some low-level utility functions that will help us with some of the cryptography. So now I can npm install and this SECP256K1 thing that you see being installed is the cryptography library that Ethereum uses to generate wallet addresses from private keys. And now that that's done, I'm going to split these windows apart. I'm going to open Node, and I will instantiate a Web3 object. So I will set var web3 equal to require web3. And then I will make a new instance of this, new web3. So I have my web3 object, and we're good to go. So the first thing that you need to know is that an Ethereum private key is a 64-character string. And any 64-character string is a valid Ethereum private key, with a couple of very rare exceptions. For example, 64 zeros in a row is not a valid Ethereum private key, but pretty much anything other than that will work. So for example, if I do the string 1 and then call the function repeat 64 times, this string is a valid Ethereum private key. Likewise, if I did 1234.repeat 16, this is also a valid Ethereum private key. If I did 1 ABC, repeat 16, this is a valid Ethereum private key. And when you generate private keys, the capitalization does not matter. So 1 ABC capital, even though this is a different string, these are the same private keys. They will correspond to the exact same wallet address. Okay, now when you have a private key, there is a deterministic function that maps a private key to a public key. So the same private key maps to the same public key every time. Let me copy this string and open up a tool that I wrote to help us visualize this. So if I paste in this private key and click generate wallet, this will actually generate the wallet address that is associated with this private key. And I can see that if I paste this in and run it again, we get the exact same wallet address. But if I change one digit, so if I make this a 2 at the end and hit generate wallet, I get a completely different wallet address. You might be wondering why the Ethereum wallet address is a lot shorter than the private key, and why we even call it a address and not a public key in the first place. So what's actually happening here is that when you do the Ethereum math to convert a private key into an address, or into a public key rather, the public key is actually quite a bit longer than this. But all that we do is take the last 40 digits of the public key and call that the wallet address. So you'll see that if I go into my node console and check the length of this string, it'll be exactly 40 digits. Now note that the 0x part of the string is not actually part of the data. This is simply a data declaration. So if you see 0x at the beginning of a string, that's simply declaring that the string that comes after is in the hexadecimal format, but the 0x is not actually part of the data itself. Now, the private key maps to the wallet address, and it deterministically does so that it does it every time. But you cannot go from an address back to a private key. It is mathematically unknown how anybody could possibly do that. You can think of it a little bit like baking a cake. You have eggs, you have flour, you have cake batter, and you put it all together, mix it up, put it in the oven, and you get a cake. You can do that. But can you go from a cake and go back to the eggs? This would be really, really hard. That's kind of what this kind of cryptography is doing. You should also note that any 40-digit hexadecimal string is a valid Ethereum address. You can send Ether to any address, regardless of whether or not it's been used before. You don't need to be connected to the Ethereum network. You don't need to register it in some service. All you need to do is perform the math to create an address, and you have created a valid Ethereum wallet. So effectively, I just created a bank account. Someone can send me money and I can use it. That's all that I had to do. I didn't need to fill out any form or give my ID to anyone or anything. It's really fucking cool. Okay, so obviously using all ones like this as your private key is a really bad idea. And in fact, if you look at the wallet address that this private key corresponds to, and I go to etherscan.io, which is the Ethereum blockchain explorer, and I'll do a full episode on Etherscan later, but if I paste in this wallet address and look at it, it's actually the wallet that somebody has used before, and there's still Ether in it. So that's how bad of a private key this is, that I just randomly generated it, and it turns out that somebody else had used it. There's actually not that much Ether in it, and in fact, there's so little that it would cost you more money to steal this Ether than the amount that it is, which is probably why no one's done it. But it does prove the point that if you pick a common 64-digit string as your private key, it's a terrible, terrible idea. So here's maybe a slightly better idea. There's a popular algorithm called SHA, S-H-A, which can hash any arbitrary string into another string of exactly 64 characters. So for example, if I did web3.sha3 and then just typed in some string here and then hit enter, it will hash that string into another string of exactly 64 characters. And if you hash the same string over and over again, it'll keep generating the exact same result. So it's deterministic, like the other function that we looked at earlier. If I change even one character in this, though, you'll get a completely different string. So that's really cool. That has a lot of interesting use cases. For example, fingerprinting documents. So you can take an entire file, you can take the SHA hash of it to get a 64-digit string, and then if somebody changes even one character in that string, you'll know that somebody altered the file because the SHA hash will be different. And in fact, you'll see places like WikiLeaks doing this. So they tweet out a SHA hash before they publish documents, and then when they publish a file, perhaps, you can look at the fingerprint of it and see that it generates this, and then know that the document is valid. So there's a lot of interesting use cases around doing stuff like that. But one of the other things that you can do is you can take a word, perhaps, that you memorized, and you can SHA hash it into a 64-digit string and use that as a private key. So let's take a look at how that might work. So if I just SHA-3 and I take a word, let's use a really simple word like password and hit enter. Now we have a string like this that I can generate a wallet from. And now here's a new Ethereum wallet, only this private key is a lot harder for someone to guess unless they knew to SHA hash this string. Now, SHA hashing a common word like the word password is also probably a really bad idea. So if you do a common word, like say I SHA hash the term hunter2, which is an inside joke from old Bash forums, and get the private key, get the SHA hash of this and use that as a private key, and generate a wallet from it, and then go to Etherscan, you'll see that, again, somebody has actually used this wallet. So just using a common phrase and SHA hashing it probably is not very secure either. These are also susceptible to things like dictionary attacks. So somebody could just loop through every word in the dictionary with a couple numbers after it, generate a public Ethereum address from it, and see if there's Ether in that address. And if there is Ether, steal it. So it's a really bad idea to use a common word like this. Maybe something that would be slightly smarter to do would be a song lyric, for example. So let's do the first line to Californication by the Red Hot Chili Peppers, which is psychic spies from China try to steal your mind's elation. And then put a seed after it, like 101, and hit enter. And then maybe we could SHA hash that. So a double SHA hash. So a double SHA hash of the first lyric to Californication with a number gets this. Maybe that's slightly more in the right direction, because this is somewhat easy to remember, but it generates something that has a decent amount of entropy. So This approach is something called a brain wallet, which means you remember some term, you remember some algorithm that you use to generate the private key from that term deterministically, and that's what you use as your secure private key. Okay, so how do you actually generate the wallet address from this private key? Like, what is this little UI actually doing? So this is where we're going to use that Ethereum JS util library. So I'm going to make a new file here called keygen.js. And what I want to do is call this file and pass in a private key and get the wallet address out, and then write the code in here to actually do that. So in Node, you can get access to arguments that you pass into a script with this process.argv object right here. So I'm just gonna console.log process.argv012 because this is an array just to see what it gives me, and then I'm gonna call node keygen.js, and I'll see the arguments that come out. So the first argument is the path to where the Node.js executable is stored. The second argument is the path to where the file is stored, and the third argument is going to be whatever we pass in. So if I called this with the term hello, you'll see that hello comes in here in the process.argv2. So we can extract the whatever argument we pass into it with this guy right here. So I am going to require the Ethereum JS util library, and I'm going to save it to a variable called futil. And then one of the really, really frustrating things about doing Ethereum development is that a lot of these libraries don't provide great user interfaces for a web developer. A lot of the low-level Ethereum functions operate on the actual byte arrays and the bytes of the data. They don't operate on higher-level structures like strings. And for the frickin' life of me, I cannot understand why these libraries don't have interfaces to interop with strings. Because all the functions in these libraries take byte arrays, and navigating and dealing with byte arrays is super frustrating. I just think it's nonsensical. So I have to always write my own little helper functions to make any of this stuff work. So here's a quick helper function called hex to bytes, which can take a hexadecimal string and convert it into the byte arrays that you need to pass into these functions. And don't worry about this too much, because I'm going to put all this code on GitHub, and you can look at it and use it in your own code base if you want. So now we want to write a function called private key to address. And this is going to be a function that takes a private key as an argument. And this is going to return the address. And then all we're going to do is console.log private key to address, and we're going to pass in process.argv2 as the argument. So all that this is going to do is it's going to write some function that can turn a private key into an address, and then it's going to log it out by passing in whatever argument we pass into the script when we call it. All right, so far so good. Now, in order to actually run this function, we're going to need to use that futil library, and we're going to call a function called private to address on the futil library. And now this takes the actual bytes of the private key. So we're going to need to use that hex to bytes helper on the private key, like that. And then this is going to return bytes, because why the fuck not? So we're going to need to convert that into a string. And we'll convert that into a string, and we want it in hexadecimal. And then we're going to put a 0x at the front of this, because it doesn't do it by default. But that code right there should actually be all that you need to generate your own Ethereum address from a private key. So now let's test this and see that if it works. So we'll do node. Let's get anything that could be a little private key. So we'll get these characters right here. And then I will run node./keygen.js, and I'll pass it in. And look, we get a private key out, and it looks like this is valid. It's 0xA8, and just to confirm as a sanity check, if I pasted, not this guy in, if I pasted this guy right here in here, we do get 0xA8. So this script looked like it worked, and this is the actual code that you need to generate your own private keys. To generate your own addresses. Now, there's actually other stuff you can do with your key pairs as well. For example, you can sign arbitrary strings of data with your private key and then verify that it was signed with the private key using the public key. That is really cool, and you will see examples of that coming later in the screencast series. We are not done with key pairs. This was just a really quick overview. One other thing to note also, even though this kind of like double SHA hashing thing has a decent amount of entropy, there are still better yet ways to actually create a Brain wallet if you wanted to put any kind of significant amount of money in this. One way to do it is using this Ethereum.js Keythereum library that has some better cryptographic functions to actually create your Brain wallets than the one that I did. You could also look at the BIP32 algorithm. This stands for Bitcoin Improvement Protocol. And this is the algorithm you see that always generates those like 12-word phrases that are like duck, horse, battery staple kind of thing. Those are good too. I kind of think those are redundant because I can never remember those, so I need to write them down anyway, and that kind of defeats the purpose of having a Brain wallet in the first place. But you'll see this algorithm used a lot. So anyway, that's Keypairs. Go on to the next video if you want to continue on.